This is lecture 14, and lecture 14 we're going to change topics from topics we've been talking about for quite some time, and we're going to start talking about convergence of random variables. The idea with talking about convergence of random variables is we've developed pretty robustly some theory about estimators, and what we want to do now is we want to develop some of the properties of them. One of the other kind of classes of properties that we can study is kind of the large sample properties of these estimators. What happens when we start taking n, the number of samples, really, really large? And that's basically gets into the realm of limits and convergence. And so this will start to feel a lot like maybe a second semester calculus or a analysis class. For the next couple lectures, where we're trying to define what convergence means in terms of random variables. And then we'll come back and we'll start talking about some of the large sample properties or asymptotic properties of some of the estimators that we've developed so far. So that's basically the roadmap, and for the next couple lectures, we're going to talk about convergence. Before we talk immediately about convergence, we should take a short little jaunt and talk about inequalities for random variables. So we'll spend the first bit of our lecture today talking about inequalities. And there are kind of two main inequalities we want to cover. One of them is a kind of general case, but one of them is a more useful kind of subcase. And the simplest and powerful inequality for random variables is called Markov's inequality. So Markov's inequality can be stated fairly simply. It says that if I have a random variable x, and I'm going to say x is greater than or equal to 0. This means x is a positive, or maybe we should be more specifically a non-negative random variable. And by that I mean the support of x is bigger than 0. So it has no density or no probability of taking on a negative number. I guess we could say greater than or equal to 0. So x is what we call a positive random variable. And if x is a positive random variable, then for for any number a, little a, that's positive, that is also positive or not negative, we have the following inequality. The probability that x is bigger than a is less than or equal to the expected value of x over a. So this is known as Markov's inequality, named after the famous probabilist Markov, something Markov. And the idea, you can draw this pictorially, is that if I have a random variable, and here's its support, so this is 0, and it goes off this way, and I look at, say, the PDF of this thing. So the PDF will take on some value, and it will look something like that. We don't know exactly what it looks like. And if I pick some value a, that's positive, I could look at this so-called tail probability. It's the probability of being out in this tail. So this is the probability that x is bigger than a. And as you notice that any PDF has to kind of asymptotically, eventually any PDF is going to go kind of to 0 as we head off to positive and negative infinity, because there has to be a finite area under this curve, and so we can't have it unbounded, or can't have it not go to 0. The tails have to go to 0, otherwise we wouldn't get a finite area under the curve. And because this thing kind of has to drop off, you can get a bound, and it says that the area here, or this probability, is less than or equal to the mean of my random variable divided by a. We can write a kind of short proof of this, proof of Markov's inequality. And as with many of these things, I'm going to do this in the continuous case. Although the discrete case is similar, discrete things are often a little trickier because you have to be careful about if you know less than or equal to continuous random variables. You can be very kind of sloppy with your notation. So that's why I often prove these things for just the continuous case. The proof for the discrete case is always very similar, but maybe a little more finicky, just to make sure you've dotted all your I's and crossed your T's. So the proof of this, we can start off by looking at what the expected value of x is, right? So x is our random variable that has a positive support. It's a positive random variable. And expectation, very simply, is, of course, we just integrate x by fx dx, right? So that's a 451 concept. It was long for the days when that's all we had to worry about. We didn't have to worry about complicated conditional expectations of functions of statistics, right? Just integral of x times fx dx. And of course, my random variable is has a positive support. So instead of integrating over the whole real line, we only really have to integrate over the support, which is just positive numbers, x fx dx. And I can break this up with my rules of integration, and I can say this is the integral from 0 to a plus the integral from a to infinity, right? You can break up integrals that way. Of course, my integrand is the same for each, x fx dx. And so we have these two parts. Maybe we'll call them part A, part B. And notice for A that x is positive over this region, 0 to a. Fx is a PDF, so that's certainly always non-negative. And so we're integrating the product of two kind of non-negative things over a subset of the positive numbers. And so this whole integral, a, surely is not less than 0. Because the thing we're integrating is positive or non-negative, and we're integrating over this whatever positive region. And so, you know, by simple rules of arithmetic, if a is bigger than 0, then surely a plus b is bigger than or equal to b. And so our integral here, which originally started off as just the expected value of x, that's all we're looking at, is bigger than b here, is bigger than this integral, right? Because the first integral is positive, and so the sum of the two integrals is certainly bigger than any one of them, or bigger than the second one here. Notice here that we're integrating from a to infinity. And when x is, let's say, bigger than or equal to a, well, x is bigger than or equal to a. So let me just actually just say notice here that in this integral, x is always bigger than or equal to a because we integrate from a to infinity, right? And so I can certainly say that this integral, if I replace something in this expression with something something smaller than this integral, I'll get something smaller, right? So I can always say this is greater than or equal to, I can replace that x with an a, because x is bigger than a, so if I replace it, I can maintain my greater than or equal to sign here. So I can say this is greater than or equal to the integral of a f of x dx from a to infinity. And a is a constant, it doesn't depend on x, so I can certainly pull that out. And I just get the integral from a to infinity of fx dx, and we have a name for that. That's just my probability that x is bigger than a. And so what I get here at the end of the day here is A times the probability that X is bigger than A. And what did I start off with? I started off with, all the way back up in my chain, it's just the expected value of X. So altogether, I get that the expected value of X is bigger than or equal to A times the probability X is bigger than A, or Markov's inequality, which is that the probability X is bigger than A is less than or equal to the expected value of X divided by A. And that's what I wanted to show. So that's what we call Markov's inequality. And it's a way of bounding this kind of what we call a tail probability here. So Markov's inequality is a very general inequality. There's a particular special case of this, which you may have heard before, but if not, we'll hear it now. And that is called Chebyshev's inequality, named after another Russian, I believe, probabilist, Chebyshev. And so let's write that out. Theorem. Chebyshev's inequality. Don't have to worry too much about spelling Chebyshev's name right, because of course it's not written in Roman characters, so it's all transliteration from Cyrillic. So actually, if you look up and read old, very old stats textbooks, you'll see this with 2 F's at the end, or Kolmogorov with 2 F's at the end. Anyways, so Chebyshev's inequality says that if I have a random variable, and now is a random variable, and I'm not going to say it's necessarily a positive random variable, which is interesting because I've said this is kind of a special case of Markov's. And let's say that the mean is called mu, so the mean of X is called mu, and the variance of X is called sigma squared. So it has a mean mu and a variance sigma squared. Chebyshev's inequality says that probability, absolute value of X minus its mean over the standard deviation, the probability that is bigger than or equal to some value K is less than or equal to 1 over K squared. So that's the statement. Let's look at pictorially what that means. So here is I'm going to draw a PDF. So let's say the PDF. Yeah, I mean, everyone always likes to draw these normal PDFs. Not everything's normal, right? You can have some weird thing. We don't really care exactly what it is. Maybe that's the PDF. Okay. And it has some mean. Who knows where it is? Maybe the mean is over here. Let's call it mu. And it has some standard deviation, and we can look, one way of rewriting this here is that the probability absolute value of X minus mu, greater than or equal to K sigma, or sigma K, one can rewrite it this way. And so, for example, if how do we want to write this? Our example is maybe 2. That's the example we want to give. Yeah. Whatever. So there's something. It doesn't really matter. It's you can think about going some K standard deviations away from your mean. So here is kind of our interval, mu minus sigma k to mu plus sigma k. And that's basically what we're looking at here. If the probability that we're outside, so this is kind of the probability we're looking at. And it says that this probability in this region here, maybe I'll do it in red to distinguish it. This probability is less than or equal to 1 over k squared. That is, we never have more than 1 over k squared probability k standard deviations from the mean. So that's, you can flip it around. You say the probability that we're within k standard deviations of the mean is always bigger than 1 minus 1 over k squared. So you can kind of flip that around. Either way you want to look at it, it's saying something about the probability you're within certain distance from the mean. So this is kind of nice. It's it's reminiscent of like a z-score from say an intro-stats course, and it's bounding the probability. Now we said nothing in particular about a random variable other than it has some mean and it has some variance, and so this is true for all random variables. And the proof of Chebyshev's inequality. Again, remember this is Chebyshev's inequality. The proof just pretty much follows directly from Markov's, which is why I introduced it first, because Markov's, if you know Markov's inequality, proving Chebyshev's inequality is really simple. So here's our proof. Let y be x minus its mean squared over the variance, sigma squared, and a be k squared. We should notice some things. First of all, we can notice that y is a non-negative random variable. Probably should be able to apply Markov's inequality to it, right? Y is non-negative because it's a square, right? It's a square or something. It's never going to take on a negative value. Everything in it is squared. And so by Markov's inequality, right, which we laid out up here, probability, a positive random variable is bigger than a is less than or equal to expectation over a. And so by Markov's inequality, if we have that the probability, let's say y is bigger than a is less than or equal to the expected value of y divided by a. Of course, we know what some of these things are. This is the probability that x minus its mean squared over sigma squared is bigger than a, which is k squared. And that is less than or equal to, well, we need to calculate the expected value of y. Expected value of y is the expected value of x minus its mean over sigma squared, or x minus its mean squared over sigma squared. Now, certainly we can pull out that sigma squared. So it's 1 over sigma squared by x minus its mean squared. And you may have forgotten, but we have a name for this. What is the expected value of x minus its mean squared? We call that the variance of x. That's just textbook the definition of what the variance of x is. And of course we know that the variance of x is sigma squared. So we get 1 over sigma squared by sigma squared, or 1. So our expected value of y here is 1, and of course a is k squared. So we can go one more step here, which is that the probability, we could just take a square root of the both sides of this, which is if I take square root of x minus mu squared, I don't get x minus mu, I get absolute value of x minus mu. Take the square root of sigma squared, I get sigma. And I take the square root of k squared, I get k. K has to be a positive number here. And that is basically Chebyshev's inequality. I guess I had a greater than or equal to here, but it doesn't really matter, certainly for continuous random variables. Okay. I guess to be consistent here, maybe I should rewrite Markov's with a greater than or equal to. I think that will make it actually be correct for discrete random variables. So let's just make sure that's consistent, greater than or equal to. Blah, 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 blah. None of this proof really matters because I did it for the continuous case. Blah, 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 blah. Okay, so now that should be right. So now these kind of match up. Okay, for this continuous, it's irrelevant, but I think that makes it proper for discrete random variables. So that's Chebyshev's inequality. And it gives us kind of a bound on how far random variables are away from the mean, but it's basically just a rehashing of the Markov's inequality. So let's just, there's a couple ways you will see Chebyshev's inequality here. I guess I should make that greater than or equal to. So various forms of Chebyshev, and they're all equivalent. So there's the canonical form, which I wrote, and just depending on what textbook you read, they'll write in different forms, but they're all equivalent, and we'll see that easily. So this is the form I wrote in. You could, of course, look at the complementary probability, which would say that the probability that x minus mu over sigma is less than k, which would be 1 minus the top probability. That would be greater than or equal to 1 minus 1 over k squared. So I can basically take 1 minus each of the first form, and of course my inequality sign flips, and I get the complementary probability. But these are kind of the same thing. I'm just looking at the probability that x minus mu over sigma is bigger than k, or x minus mu over sigma is less than k, right? And there's their complementary, so either less than 1 over k squared or greater than 1 minus 1 over k squared. Okay, not too bad. You can also kind of reparameterize this. So if I sometimes you'll see this, and this will be useful when we talk about convergence, where sometimes people will say epsilon is k by sigma, or that means that k is epsilon over sigma, right? And 1 over k squared is sigma squared over epsilon squared. So purely a reparameterization of the problem. In this form, if I take my first one, this would say, so k sigma, so if I move my sigma over, we would get a form of absolute value of x minus mu greater than or equal to k sigma, which we call epsilon, is less than or equal to sigma squared over epsilon squared. So that's another form you'll see it, and that's might be particularly useful for our convergence of random variables. The kind of equivalent way you will see this is you could also take 1 minus this, and you could say the probability that x minus mu is less than epsilon is greater than or equal to 1 minus sigma squared over epsilon squared. So knowing these kind of 4 forms, there's only really 2 different forms are useful, but they're all equivalent, and it's just a reparameterization, because we will see that calculating this probability x minus mu is greater than epsilon is something we're going to be interested in for convergence of random variables. So before we move on to convergence, I should do my duty here and just look at one example of how to use Chebyshev's inequality outside of a convergence context. So here's an example. Let x be the number of nails in a manufactured how do you spell manufactured? See, if you write it sloppily enough, no one can tell if you can't spell. In a manufactured box by some factory. Right, so this is kind of very much a quality control problem, right? So x is the number of nails produced by a factory. There's supposed to be a certain amount. There's supposed to be maybe 1,000. So on average, the mean number of nails I put in the box is maybe 1,000. And the variance for the number of nails I put in the box is, let's say, 25, which is pretty large. But so the standard deviation would be 5. And I could ask a question. I don't know anything about the distribution of these, but here's a question. What is the probability that the number of nails that actually end up in my box is, say, between 994 and 1,006? That's 10,006, 1,006. So how might I calculate this? I don't know anything. I don't know anything about my distribution. So I basically want to calculate the probability that 994 is less than or equal to x is less than or equal to 1,006, which is the same thing as saying the probability. So this is, 1,006 is 1,000 plus 6, 994 is 1,000 minus 6. So this is the same thing as saying the probability that x minus 1,000 is less than or equal to 6, right? And I could, of course, divide through both sides of that inside my probability by the standard deviation, right? Sigma is 5. So I could say, what's the probability that x minus 1,000 divided by 5 is less than or equal to, what, 6 divided by 5, 1.2? So can we say anything about that? Well, this is my mean, this is my variant, or my standard deviation, x minus mu over sigma less than or equal to 1.2. If I go to this first form here, nope, I want to go to my second form here. That should be greater than or equal to 1 minus 1 over k squared. So this should be greater than or equal to 1 minus 1 over, what's k? This is basically k. And I won't do the actual calculation. Something like 0.3055 or something like that. So about 30%. So I don't know, it depends on how good you want your tolerance, if that's a good answer or not. But the probability that we're within about 1.2 standard deviations, 30%. Maybe not so good, but that's a way you can use Chebyshev to calculate probabilities. And we bounded this probability, and we don't need to know anything about that random variable. So that's gonna be true for any distribution, as long as we know its mean, its variance. We can bound that probability. That's really useful in the practical sense when in reality you'll have, you're not handed from on high this thing is Poisson. No, you're handed some data and you're asked to, by your boss to, make sure the probability that we lose a bunch of money in this proposition isn't more than X, Y, or Z. And here's the calculation you do, and it doesn't really matter what the underlying distribution is, as long as you have a good sense of what the mean and the standard deviation are. So this is something that's super useful. Okay, so that's inequalities. And we're going to put those aside for a little bit, but I wanted to kind of prep the groundwork for some of the homework problems on this. And we're going to talk now about convergence of random variables, and that will take up the rest of the lecture. So here's where we get back into Calc 2, or analysis. Right, in Calc 2, we spent all this time talking about convergence of sequences, right? Sequences and series. So Calc 2, what we did is we talked about convergence of sequences of numbers, some xn's, and we said they go to x, right? And here we had xn and our limit, which is what's called x. Those are numbers, right? And people take Calc 2 and they don't really understand why you spend so much time talking about sequences and series until you get to either this class or an analysis class. Analysis is basically probability with less restrictions, but and it turns out these are kind of really central topics to all of the way you actually talk about this stuff. So that's Calc 2. 452, we're going to ramp up the fun here, and we're going to talk about now sequences of random variables and convergence of random variables. So we have some xn that converges to some x. But now, instead of xn and x being real numbers, xn and x are random variables. And so we're going to have some fun talking about all that. And as I said at the beginning of the lecture, this is going to relate back to basically anything like you can talk about, say, a central limit theorem or a law of large numbers, or some people call it the law of averages, which is not a term statisticians use, but basically the idea is that if you want to precisely state those things, you have to talk about what happens when things get really large, which is basically the realm of convergence. So in order to talk about convergence of random variables are much richer objects than numbers. They can be viewed as functions, but they also have all these other associated things. They have PDFs, CDFs, MGFs, and all this stuff. And so there are going to be many different kind of ways we can talk about convergence. And so we're going to talk about some of the most useful and most commonly used ways of talking about convergence of random variables. But fundamentally, what we have to recall, so in the most basic form of convergence, recall that a random variable, xn, is a function. It's a function from a sample space S to the real numbers, right? At least a univariate random variable is that. And, right, so for some S in their sample space, right, we haven't talked about sample spaces since 451, right? First F 451, but ultimately random variables are just functions, and they say for some little s in my sample space, we calculate x of little s, and this is a number. And so we can talk about convergence of random variables as convergence of functions. And that's what we're going to do for the first little bit here, at least for half a minute. We're not going to extensively talk about this. This is really a functional, not purview of a functional analysis class. But let's just give one definition about convergence of functions. And we're going to define pointwise convergence of functions. So forget probability, thank God. Forget math stats. Whew. Let us have some sequence Fn. So let Fn be a sequence of functions. And maybe I should not have curly brackets. Maybe it should be something like that. Fn is a sequence of functions. So that's my way of denoting a sequence of functions. Right? N goes 1, 2, 3, right? It's a sequence of functions Fn. And let's just say they're real valued functions. It doesn't really matter that much, but they're real valued functions. And f is some other real valued function. The limit. We say, this is like day one of a functional analysis class, we say the sequence of Fn's converges pointwise to f. So these Fn's converge pointwise to f if for any x, for any number x, Fn of x converges, so my arrow here is converges to fx. So my arrow here means converges. Probably should have explained that above, right? This arrow just means converges. It's the more big boy version of writing the limit of whatever. So pointwise convergence of functions is basically if I take one x at a time and I look at f1 of x, f2 of x, f3 of x, f4 of x, right? And I increase my little index for n. If that sequence of real numbers converges to f of x for any possible x I choose, that's called pointwise convergence. Let me draw it out. So notice here that if I fix my little x, that thing's just a number. Fn of x is a number, and so is f of x. It's just some number. And so if I fix my x, let's say fix x, we can talk about convergence of these things as just convergence of numbers. We can look at f1 of x, f2 of x, f3 of x, f4 of x. You know, maybe let's say x is 5, right? Let's just pick a number. So you got f1 of 5, f2 of 5, f3 of 5, f4 of 5. And you can do this, and if this converges to f of 5, you know, this converges as a sequence of numbers. Okay, we'll put that aside, and then we go for another x. Let's say x is equal to 6, and f1 of 6, f2 of 6, f3 of 6, converges to f of 6. Again, as a sequence of numbers, this is just a number. F1 of 6 is a number, F2 of 6 is a number, and so it's just like an xn. You know, it's just back to our Calc 2 definition here, right? And if we get convergence, where for any x, you know, 5, 6, 1, pi, e, 1.7, right? If I look at the sequence as I increment my index of my function here, if I look at that sequence and that converges to f of the limit function, evaluate that same thing, we say that we have pointwise convergence. So all pointwise convergence is basically you just treat, you fix the x and then you treat the thing as a sequence of numbers. That's day one of functional analysis, pointwise convergence. Maybe not day one, but day two. So pointwise convergence of functions. And why do I bring up pointwise convergence of functions? Because we said random variables are functions. And so because statisticians like to be hard or probabilists, I can blame this on the probabilists, yeah, because the probabilists they're awful, right? And they want to make our lives hell. We give this a new name when we're talking about random variables, and we call this sure convergence. So our first, very, very, very first convergence topic is called sure convergence of random variables. We say that a sequence of random variables, x1, x2, x3, dot, 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 converges surely to some other random variable x if, and the notation here is typically what we do is you write PTWIC or something like pointwise to denote that that's pointwise convergence. No, we don't. We write it here. Let's say denoted as the side. Typically, we'd say that Fn converges to F pointwise. All right. So that's the notation for pointwise convergence. It means that for each x, it converges as a sequence of numbers. So for a sequence of random variables, we say they converge surely to some other limiting random variable x if my xn's converge pointwise to x. So what that means is that for all little s in my sample space, if I look at xn of little s, this is going to converge to x of s as a function. Nothing here about probabilities yet. Literally just as functions. So oftentimes people skip over sure convergence when they talk about convergence, but I think it's useful to bring in the functional analysis part here, connect it up. So it doesn't really have much to do with probability because you notice this definition has nothing to do with, there's no probability in there. So once this is, it's just a renaming of pointwise convergence of functions. So here's where my mantra about probability will come in. We can define sure convergence, which typically people just kind of gloss over and don't even define it, and they skip right ahead to what we're more interested in, which is called almost sure convergence. And almost sure convergence is we say a sequence of random variables, let's say xn, that's my notation for sequence of random variables. Say a sequence xn converge almost surely to some other limiting random variable x if let's say the xn converge surely to x on some subset, let's say A of S. So they don't converge, maybe we should not say converge surely, maybe we should say converge pointwise on some subset A. So they don't converge for every possible S, but they converge on some subset of my sample space that is sufficiently large. So the set on which they converge has probability 1. So we say they're almost surely converge because they can converge surely almost everywhere. Where'd they not converge surely? Well, there's some subset of probability 0 where they might not actually pointwise converge. But we don't care because we're sloppy, we're probabilists. So probabilists are just analysts that don't care about sets of probability 0. So that's the joke you'll hear. And this is exactly that scenario, right? If you ask a function analysis person, they'll say, they'll talk about pointwise convergence. And sure, we care about pointwise convergence, but we don't really care about sets with probability 0 because they don't happen. They don't occur. Who cares? So probabilists basically say, we don't really care about sure convergence or pointwise convergence. We care about things that almost surely converge, which is that they converge pointwise with probability 1. Our notation here is that we write xn arrow x, and we write a dot s over it for almost surely. So almost sure convergence means that, so basically, almost sure convergence is pointwise convergence on everything, let's say everywhere, in S except maybe some small set, I don't know, E with probability 0. So it just allows us to be a little more loose because we don't really care about things sets with probability 0. And so almost sure convergence says that it's basically kind of pointwise convergence of these random variables of function, except we can ignore anything, any set with probability 0. We don't really care if it converges there or not, because if the set is small enough where it doesn't pointwise converge, who cares? It doesn't really happen at all anyways. So one quick way to summarize this, or maybe two quick ways to summarize this, is basically you could say xn of s converges to x of s for all s in some set A where probability A is 1. That's the kind of real shorthand notation for convergence, almost sure convergence. One nice way, so I'll put a pin in this. So this is going to seem strange, but we'll see why this is interesting in a minute. Another way to think about this, I'm not going to prove that this is true, although I think it's not too bad, is that another way to think about almost sure is that if I look at any epsilon bigger than 0, so let me pick any small epsilon and consider some event E, n, which is the event that xn minus x is less than epsilon. So epsilon is just some small number. And I'm going to consider the event, this is kind of my notation for it. I'm going to consider all s's, this is some event, all the event that xn, the absolute value of the difference between xn and its limit is less than some small number, right? So this is more formally, it's all S in my sample space where xn of S minus x of S is less than epsilon. But this is just some event. Okay? And I'm going to define the limit as n goes to infinity of these events, of these East events, which is the limit as n goes to infinity of, we could say, xn minus x less than epsilon, right? So the limit of this. And we're going to define that as the union of the East events, right? So it's basically the union of these events. Let's say, over all possible n. So let's draw a little picture about what these things look like. So here's maybe my sample space. And there can be some event, let's say E1, which is the event that x1 minus x is less than epsilon. I've chosen my epsilon in advance, and there's there can be some place in my sample space where this is going to be true, where x1 is going to be close enough to x, and some place where it's not going to be true. So maybe that's that event. And then I can look at E2, which is x2 minus x less than epsilon. And that's a bigger event. It's going to be nested in that way, typically, let's say. And I could look at E3, and that's gonna subsume those two. So why are they nested in this way? Well, if we believe that as we increase n, the x's get closer to x, the xn's get closer to x, the probability that we're close to, that xn is close to x, say, and by close I mean less than some threshold epsilon, should be increasing, right? And so the kind of space, the collection in the sample space should be kind of increasing as we go this way. And so if the limit of this is basically the union of all these things. And if we define it, and the kind of real PhD level class, you would more properly define that. We're not in that class. And this is kind of just an interesting aside, is that it is equivalent to say that, let's write it like this, xn converges almost surely to x is equivalent to saying that the probability of this limit, as n goes to infinity, of xn minus x less than epsilon is 1. So saying that something converges almost surely to x is saying that these nested set of events eventually subsumes a large enough portion of the sample space that the probability we're in this ever-growing nested collection of sets eventually kind of subsumes the whole space. So this thing grows enough. So alternatively, you could say that the probability of the limit as n goes to infinity of xn minus x is bigger than or equal to epsilon is 0. So either way is that the probability of that we're less than epsilon away eventually becomes 1, or flip side, the probability that we're further away than epsilon goes to 0. which in some ways, both of those things seem to imply some kind of limiting behavior that in the large, and for large enough n, we're going to be sufficiently, the x of n is going to be sufficiently close to x. So the more useful definition is this first definition. It's probably even just this really short definition at the end here. This is an interesting way of thinking about it, and we'll come back to that in a little bit. But let's look at maybe an example. Unfortunately, examples of convergence at this point are kind of contrived because this is still very abstract. So here's our example. Let S be our sample space, and let's just take it as a unit interval with uniform density. Basically a uniform random variable, but we won't get into that too much. And let xn of S be S plus S to the n, right? So a random variable, though we may have forgotten it, is just a function from my sample space to the real numbers. So this is a function from my sample space, which is the unit interval, to the real numbers. And it's S plus S to the n. That's x of n. And our limiting random variable, x of s, we're going to say is just s. So that's just the identity function on this unit interval. Wonder if I can draw a picture of these. I think I can draw a picture. Am I smart enough to draw a picture? What does s to the n look like? I think I can draw a picture. We'll see. So here's our unit interval. And we could look at x of s. So we have s here. This is like our sample space here. It's our s-axis. And then we have xn of x of s. Oh my god. And here's maybe our 45-degree line. So the limiting random variable is just this identity function. Map 0 to 1 to 0 to 1. So that's my x. All right. And my my x of n, what does this look like? Am I smart enough to figure out what this looks like? It's that plus something, so surely like above this 45-degree line. And so it's going to lie somewhere up here, right? Where exactly is it going to lie? At 0, let's just do this. This is like a high school problem. At 0, what's the value? At 0, it's 0, so it's certainly going to hit that point. At 1, it's 2, right? So it's going to somehow hit up here. That's somehow 2. And then it's always going to lie above this line, so it's probably going to go something like that. Probably looks something like that, right? Okay. But it lies above that line. And so as we imagine that as we increase n, this is going to hopefully start to look like our identity function. And this is kind of bend down, down, down. These points are going to kind of converge to this line here. So that's the intuition. Notice here, so we can ask, does xn converge almost surely to x? Well, what does that mean? Notice that if my little s is between 0 and 1, but not including 1, then xn of s, which is s plus s to the n, is going to converge to s, which is x of s. Why? If s is between 0 and 1, right? So take s is 0.5. What's s squared? 0.25. What's s cubed? 0.125. S cubed, right? The fourth power, right? It gets smaller and smaller and smaller. So if I take a number between 0 and 1 and I raise it to successively higher powers, it's going to get smaller and smaller and smaller and smaller and smaller, right? And so if I fix my little s and I just increase n, this second part here is going to go to 0. As n gets larger, that thing goes to 0, and I'm just left with my s, and that is exactly x there. So for any point between 0 and 1, not including 1, that's going to be true. However, if s is equal to 1, then xn of s is, I think, always 2, right? It's 1 plus 1 to the nth power, which is, right, it's 1 plus 1 to the n, which is always 1. That does not converge to 1, which is x of 1, right? Xn of 1 is 2, x of 1 is 1, and xn of 1 is 2 always. So you never get convergence there. You get this pointwise convergence for s between 0 and 1, but not when s is 1. We don't care. The probabilist says, who cares? All right? The probability that xn, so this is one way I tend to write this, is that xn of s converges to x of s is 1, right? Basically, the set, if I look at A, which is the set of my sample space where we get pointwise convergence, xn of s converges to x of s. In this case, this is everything between 0 and 1, but not including 1. And if I have, as I claimed, I have a uniform density on my sample space here, then the probability of A is 1. We don't care that, you say, we're not bothered that, the probability that it doesn't converge on 1, how do I say this? We're not bothered that we don't get no convergence when s is equal to 1, because the probability of being there is 0, and so we just ignore it. So in this case, we do get almost sure convergence. To answer the question, yes, it does converge almost surely, because it converges everywhere between 0 and 1 except for 1, but 1, the probability we're in that tiny little set is 0, so we just say, yeah, whatever. Who cares? So that's the difference between a person who does analysis and a person who does probability, is the probabilist just ignores it. So in the last couple of minutes, we can talk about, we'll start talking about the next convergence, type of convergence. Unfortunately, unlike a Calc 2 class, we don't just have one type of convergence. Almost sure convergence it turns out is a strong condition. It's a pretty strong condition to require that something converges almost surely, because it basically has to converge for every point except for some tiny, tiny, tiny little set, right? So it's generally difficult to establish. And for many sequences of random variables don't converge almost surely, because it's a really kind of strong condition. Sometimes we can't establish that a sequence converges almost surely, but we can establish a weaker form of convergence. And the first weaker form of convergence we're going to talk about is called convergence in probability. Convergence in probability. We say a sequence xn converges in probability to some limiting random variable x if, or we should say denoted, so our notation for this is xn over arrow p x, so the p here stands for in probability. We say that this xn converge in probability to x if the limit as n goes to infinity of the probability, let me back up here, if for all potential thresholds epsilon we can choose, the limit, it's supposed to be a comma, the limit of the probability that xn minus x is less than epsilon is 1. So what is this saying? It's saying that I'm going to choose some threshold epsilon, and I'm going to look at the situation where at some point in my sequence, xn is the distance of xn to x. I'm going to say, how far is xn from x? Is it less than my threshold epsilon, or is it not? And convergence in probability says, if I go further enough out in my sequence, eventually that probability is going to hit 1, at least in the limit. In a limiting sense, it can hit 1. So let's put a line there. That's the formal definition. One can think of it as, first thing I'll do is, let's just say we pick some epsilon, some threshold. And this has to be true for any threshold we choose. But so let's pick our threshold, and we're going to calculate the probability that x1 minus x is less than epsilon. Some number. Maybe it's high, maybe it's low. Then we're going to calculate the probability that x2 minus x is less than epsilon. So let's calculate the probability that x2 is more than epsilon, or is less than epsilon from x. Then we're going to calculate the probability that x3 is less than epsilon from x, and so forth. And we can do this out to infinity, and this sequence of probabilities should, in its limit, achieve 1. So you can think about drawing a graph here, where on the y-axis I have the distance, the probability that xn is less than epsilon from the limit, capital X, and there's probabilities between 0 and 1, and then I'll increase n on my x-axis, and I'll, for different values, I'll calculate for x1, what's the probability? Maybe it's low. The probability that x1 maybe can be far from x, and maybe x2 can be a little higher, and so maybe my sequence looks something like this when I calculate these probabilities. But there's some asymptote here, 1, and eventually this sequence, which is just a sequence of numbers, has to asymptotically, or in a rigorous sense, in the limit, that thing has to hit 1. And the idea is that if I go further enough out my sequence, the probability that xn is within epsilon of x is 1. I can make the probability xn is less than epsilon away from our limit arbitrary close to 1 by going further than the bound by sequence. That's the rigorous way of saying it. An equivalent way of writing this, and I'll stop on this, is that we can instead of looking at the probability that we're less than epsilon, we could look at the probability that xn is more than epsilon away from x. And if the limit that xn is less than epsilon away from x has to be 1, then the limit that xn is more than epsilon away from x is going to be 0. And that, the alternative way of thinking about it, the kind of flip side, which is just taking 1 minus the probability on each side, is that if I go further than the bound by sequence, the probability that xn is more than epsilon away from x goes to 0 in the limit. So if I want to drive that probability down to 0, I can go sufficiently far out into my sequence and I'll eventually get it. So this is our second definition. We'll pick back up here next time, called convergence and probability. And we'll see it's a slightly weaker form of convergence and is related to our convergence in our almost sure convergence in some way. Okay, but we'll stop here for now.